Welcome to Signal Ahead. I'm Alfred. Today's briefing, Theory and Foundations, Physics plus Math. Monday, July 27. This is the synthesis above the noise, not the headlines, but the deep currents beneath them. Let's get into it. There's a paper making the rounds among people who follow the deep foundations of physics, and its subject is something called Jordan triples. Now, that phrase means nothing to most people, and I confess it would have meant little to me some years ago. But here is the thing worth noticing. The thread I want you to hold on to for the next hour. The most interesting frontier in fundamental physics right now may not be a bigger machine or a fainter signal from a colliding pair of black holes. It may be a piece of 19th and 20th century algebra that was invented, essentially, to fail, and whose failure turns out to encode the structure of the particles that make up everything you have ever touched. Let me explain what I mean, because it's the sort of connection a casual reader of the science pages would sail right past. Back in the 1930s, physicists were hunting for a new arithmetic of quantum observables, a way of multiplying measurable quantities that respected the odd rules of the quantum world. They found a candidate, an elegant symmetric product, and they classified all its possible forms. And it was a disappointment, because almost all of them turned out to be nothing new. They were just ordinary matrices in disguise. All except one lonely exceptional case, built from the octonions, the strangest of the number systems, the one where multiplication refuses to be commutative or even associative. For decades, that exceptional structure sat in a corner of mathematics like a beautiful object with no purpose, admired and unused. And what the recent work suggests is that this discarded, exceptional algebra extended into a richer thing, a pair of these structures woven together, reproduces, with startling economy, the gauge groups and particle content of the standard model. The very symmetries that took generations of experiment to pin down, the electromagnetic, the weak, the strong. The dead end became a doorway. That's the shape of the argument I want to trace, that the state of the field at its foundations is increasingly a search not for new phenomena, but for the right mathematical language, the conjecture that reality is, at bottom, picking out one particular exceptional structure and asking us to notice. Now, if that were an isolated curiosity, I wouldn't hang an hour on it. But look at what else is stirring in the same season. There are people rewriting the gravitational path integral in the language of quantum reference frames. The idea that there is no view from nowhere, that every observable must be dressed relative to some physical frame built out of the fields themselves, and that when you do this honestly, the ghosts and anomalies that plagued the old gauge-fixing procedures simply dissolve. There are people studying matrix models, great arrays of non-commuting variables, and asking a very physical question. Under what conditions do those matrices stop being an abstract soup and start behaving like the coordinates of an actual space? The remarkable finding is that empty space, commuting coordinates, is entropically disfavored. It takes fermions, and a precise critical number of them, to tip the balance and let geometry crystallize out of algebra. Space itself in these models is not assumed. It is earned. You see the common melody. In each case, the frontier is conceptual and mathematical. Where does spacetime come from? What is the right invariant, frame-independent way to ask a physical question? Which exceptional algebraic object does nature actually instantiate? These are not questions a collider answers. They're questions you answer with a piece of chalk and a great deal of stubbornness. But I want to be scrupulously fair, because there's a countercurrent, and it matters. There has been a quiet, bracing dispute over whether the celebrated demonstrations of quantum advantage, the claims that a quantum device did something no classical computer could match, have quietly been walked back, reproduced on ordinary machines within a year or two of the fanfare. The sober response is that this misreads the situation. The goalposts were never that a demonstration stay unbeaten forever. The hardware and the classical algorithms are racing each other, and that race is exactly how progress in this era is supposed to look. The lesson for us is a humbling one. Foundations can be seduced by elegance. A beautiful structure, an exceptional algebra, an emergent geometry is a hypothesis, not a discovery, until something outside the mathematics confirms it. The history of physics is littered with gorgeous frameworks that described nothing. So here is where the field stands, and here is our argument. On one side, an extraordinary flowering of mathematical ideas that promise to derive the furniture of reality particles, forces, space, from pure structure. On the other, the discipline's hard-won knowledge that elegance is not evidence, that even our newest tools can flatter us. Over the next while, I want to walk both sides of that line, to take the octonions and the matrix worlds seriously, and to ask, honestly, how we would ever know if any of it were true. There's a temptation, when you look at a week's worth of new physics and mathematics, to see only a jumble. A paper on the strong coupling limit of matrix models sits next to a computation of algebraic K-theory groups, which sits next to a story, I'm not making the title up, about a tipsy kangaroo hopping through the space of gravitational wave models. It reads like a bazaar, everyone shouting about their own particular wares, no two stalls selling the same thing. But if you stand back and squint, a current runs underneath all of it. And the current is this: the deep work of our era is not the discovery of new objects. It is the discovery that objects we thought were different are, at a structural level, the same object wearing different clothes. The real trend is translation, the patient construction of dictionaries between languages that once seemed to have nothing to say to one another. Consider the impulse to describe the standard model of particle physics using an algebraic structure, a system of triples, of paired elements obeying certain multiplication rules. Now the standard model already works. Nobody needs a new formalism to predict what comes out of a collider. So why do it? Because the particular way the known particles arrange themselves, 3 generations, these peculiar charges, this exact gauge group and no other looks, in the ordinary language, arbitrary. A pile of facts, but if you can show that this arrangement falls out naturally from an algebraic structure that mathematicians were already studying for entirely unrelated reasons, then something has shifted. The arbitrariness dissolves into necessity. The list of facts becomes a theorem. That is the whole game, not adding to the pile, but finding the shape the pile was always secretly forming. You see the same instinct in the correspondence between three-dimensional gauge theories and knot complements, the study of the shapes left over when you remove a knotted loop from space. On one side you have quantum field theory, all path integrals and partition functions. On the other, you have low-dimensional topology, knots and the polynomials that distinguish them. These are different departments, different journals, different coffee rooms. And yet the claim is that a physical quantity computed one way is literally equal to a topological invariant computed the other way. The same number, reached by 2 roads that never intersect until they arrive at the destination. When that happens repeatedly, and it is happening repeatedly, you are no longer looking at coincidence. You are looking at architecture. Even the humblest seeming problem carries this signature. Take the old puzzle of reconciling electromagnetism with fluid dynamics, one theory born under the geometry of special relativity, the other content with the older, homelier symmetries of Newton. Slap them together carelessly, and you get nonsense. The interesting work is in finding the limit, the careful passage, where one framework gracefully becomes the other without the machinery grinding. That, too, is translation. It's asking, under what conditions does this language collapse into that one, and what gets lost in the crossing? And here is where I want to be honest about the noise, because there is real noise. Not every announcement of a bridge is a bridge. We have lived through claims of quantum advantage that were reproduced on ordinary machines within a year and a half the demonstration. It turned out built to be beaten. Whether that represents a failure or simply the ordinary friction of a young field is genuinely contested, and reasonable people are shouting at each other about it. But notice what the argument is actually about. It is about whether a claimed separation, a place where the quantum world pulls decisively away from the classical, is real or illusory. It is a dispute over the exact location of a boundary, which is to say, even the fights are about the map. The counterexample to a long-standing conjecture, the Jacobian conjecture, this deceptively simple statement about polynomial maps, belongs to the same current, though it runs the other direction. Here the deep work is the discovery that a bridge people hoped existed does not in fact exist, that a plausible-looking structural equivalence fails. That is not a defeat. A well-understood counterexample is itself a piece of the map. It tells you precisely where the territory refuses to behave, and a good digestion of why it fails often teaches more than a proof would have. So the deep current is not any single result. It is a change in what counts as understanding. To understand something, increasingly, is to know what else it is, to hold in one hand the algebra and in the other the geometry, and to feel them close like a hand around a familiar object. The visualization tools people are now building, letting a machine animate the flow of a mathematical process, those are of a piece with it too. They are dictionaries between the symbolic and the visual, translation made moving and immediate. Beneath the bazaar, everyone is quietly building the same thing, a way to say at last that these two things you thought were strangers have been the same all along. Here we are then, at the part of the conversation I always find most treacherous, the moment where we ask what any of it means. Treacherous because the honest answer to what does this mean in foundational physics and mathematics is very often, we don't know yet, and pretending otherwise is how people get themselves into trouble. So let me try to draw out some second-order implications from the material we've been circling, while resisting the urge to tidy it into a moral. Start with the recurring theme that has, I think, been quietly running underneath everything, the difference between a result that is true and a result that we understand. These are not the same thing, and the gap between them is where the real work lives. Consider the digestion of a counterexample to a famous conjecture, the Jacobian conjecture, that lovely, deceptively simple claim that a polynomial map with constant non-zero Jacobian ought to be invertible. When someone produces a counterexample, the naive expectation is that the story ends. It does not. The interesting activity is the digestion, pulling the object apart, asking why it works, what mechanism defeats the intuition that made the conjecture seem obvious in the first place. A counterexample that isn't understood is barely more useful than an open problem. And this tells you something about what mathematical knowledge actually is, not a ledger of true and false statements, but a web of explanations we can hold in our heads. Now watch how the same distinction plays out in physics, where the stakes are dressed up in laboratory clothing. There has been a sharp exchange about whether the quantum computing demonstrations of the last several years, the noisy, intermediate-scale devices, and the various claims of quantum advantage, actually delivered what was promised, or whether each flagship result was, in effect, engineered to be just barely beyond the reach of classical simulation, only to be caught and reproduced classically within a year or two. This is a genuinely important argument, and notice its structure. It is not really about whether the machines worked. It is about what counts as a demonstration in the first place. If every advantage claim is designed to sit at the fragile edge of classical reach, then being overtaken classically is not a failure of the physics, it may simply be the natural churn of a moving frontier, or it may be a sign that the goalposts were placed where they could conveniently be reached. The point I want to press is that you cannot settle this by looking at any single experiment. You have to have a theory of what the experiments were for. Foundations, again, doing the load-bearing work beneath the empirical surface. Let me widen the lens to what I think is the deepest current running through the corpus, the persistent search for structure where we did not expect to find it. There is this striking proposal to build the standard model of particle physics out of Jordan algebraic structures, Jordan pairs, octonionic scaffolding, the exceptional bits of mathematics that seemed for decades to be beautiful orphans with no physical home. Whether or not that particular program succeeds, and I would counsel patience rather than enthusiasm, it exemplifies a bet that the arbitrary-looking features of nature, the particular gauge groups and particle content, are shadows of some rigid mathematical object we haven't correctly identified. The second-order implication is worth stating plainly. Much of foundational physics is now driven less by data than by the conviction that the universe should not have been able to be otherwise. That is a metaphysical wager, and it should be held as one. You see the same appetite in the matrix models, where people ask under what conditions a collection of non-commuting matrices behaves as though it describes an ordinary commuting space, as though geometry itself emerges from something more primitive, and remarkably, that fermions can tip the balance at a precise critical threshold. Space as an output rather than an input. And in the relational formulations of the gravitational path integral, where the very notion of a coordinate system is rebuilt from the field content of the theory, so that observation is always observation from somewhere by something. What to watch in all these cases is the same signal, the moment when a background assumption we didn't know we were making a fixed space, an external clock, a preferred frame, dissolves into a derived quantity. And here is the humbler thread I'll close on. Alongside these grand structural bets sits a quieter revolution in how the work gets done, the sudden ease of building tools to visualize a process, to animate a figure, to see a mathematical object move. It sounds like mere convenience, but the warning that accompanies it matters. Something that superficially resembles a finished result, produced before genuine testing and review, is a trap dressed as a gift. That, if anything, is the meaning I'd send you off with. Whether it's a counterexample, a supremacy claim, or an elegant algebra promising the standard model, the seductive thing is always the object that looks finished. The discipline, the whole discipline, is refusing to believe it until you understand why it's true. That's the signal for today. The noise will keep coming, we'll keep finding what's underneath it. This has been Signal Ahead with Alfred. Until next time.